Okay, in this video we'll begin talking about the Lorentz force law. So we're going to test this out. I'm going to basically be your virtual experiment. Now I'm going to place a positive charge, because we are pretty familiar with positive charges. Later we'll talk about negative. Place a positive charge in here and see what happens to it. Experimentally, we're going to say, try one thing, see what happens. Try a different thing, see what happens, and gradually build the Lorentz force law based on this. So the first thing that we're going to try is taking our positive charge and just placing it in there, and we notice that it doesn't actually do anything. If we just place it in a magnetic field, nothing is going to happen at all. Immediately we know that that distinguishes magnetic fields from electric fields, because if you put a positive charge in an electric field, it's going to start going, right? There will be an acceleration. Here, nothing, and that's interesting. Maybe they don't interact with positive charges. But then we find, well, if we actually give this positive charge a velocity, and let's say our velocity is in the z-hat direction, what we're going to notice is that if it starts moving in the z-hat direction, it's going to experience a force. And what direction is that force? I'm going to go ahead and tell you that it's up. We will address the directions and how to determine them in the next video, but for now we just want to kind of notice some really interesting things about this. It's moving in the z direction, and yet the force is perpendicular to the direction of motion, and that's really interesting to us. So what about if we decided to move it in a different direction? Let's try moving it in the x-hat direction. So if we move it in the x-hat direction here, again we notice that nothing happens. Well, okay. So obviously direction matters, right? And then also there's a perpendicular element to this. So we try a new thing and we say, let's move it in the negative z-hat direction, so backward along z. And we find, we might think that, well, this field produces forces upward, but this time it actually produces a force downward. So as we move to the right, then it will experience a force downward. Okay, that's interesting too. We move backward along x, nothing happens again. So we're starting to build an idea. So we say, well, okay, we know if we move it along positive z, we experience a force upward. What if we move it twice as fast? And we try it, and we find it actually experiences twice the force. Interesting. If we increase the strength of our magnetic field, then the force increases proportionally, which makes a lot of sense. So what about something that isn't on the x or y direction? If we start at the origin and we head in a direction that is both x and z, then we experience a force, again, upward. So as we move in part x and part z, we will experience a force upward. Now it's actually going to happen like that, so it's going to happen, gradually. But we can immediately see that the force, even though we're not moving along z, along x, along y, the force is still at perpendiculars. Okay, let's put this together in a mathematical sense. The force that we experience here, I will not go over the direction right now, we'll do that in a separate video, is called the Lorentz force, and it's equal to the charge value. So if we have a larger charge, then the magnetic field will interact with it more strongly, times the velocity, or the speed of the charge, times the magnetic field strength. So those three things are proportional to the force, but it also matters direction, so we will need a trig function in here. What is theta? Remember, that's always going to be your question when you deal with an equation like this, where sine theta, sine of what theta, right? Theta's got to be the angle between something and something. Well, in this case, theta is the direction, or the angle between two different directions. There's only two vectors in our equation, velocity and magnetic field. Charge doesn't have a direction, so those are actually the things that theta is between. So if you have the B field this way and the velocity this way, then the angle is actually going to be between the velocity and the B field. Okay. Now notice what this means in terms of trigs. So sine theta, remember, has to do with the opposite side over adjacent. Sine has to do with perpendicular things, and cosine has to do with parallel things. So if we approach 0, we say the sine of 0, we know that's 0, so that means that you would zero out the entire force, which means that if you're moving along the x-hat direction and the B field is moving along the x-hat direction as well, you're not going to experience any force. But if you were to move along the z direction, then you have sine of 90 degrees, which is 1, which means you get the absolute maximum effect. All of these variables are at their strongest when you're moving at perpendicular angles to the magnetic field. Now, to make sure that we're clear about something, this does not mean that if we were to change our direction of motion that it's always going to have a force along x, y, or z. That's not necessarily the case. Let's give another example. If we were to move in the direction of the z and the y direction, so let's have a velocity in that direction, part z, part y, then we're still moving so that our velocity is at a 90-degree angle with respect to the magnetic field. We will get absolutely full strength of the Lorentz force, but the direction will change. And again, we'll talk about direction in the next video. But this is a pretty easy equation to use. Just like with some of the other things that we've been through, like flux or torque or any of that, it's really a matter of angle. That's the hard part, right? Understanding what the angle is. Okay, so let's try some. To proceed, we should simplify our discussion because a lot of this is actually going to be viewed in 2 dimensions, especially in your homework. So I wanted you to be aware of the 3-dimensional nature of this, but we can actually represent this in 2 dimensions as long as we give ourselves conventions for the directions. So everybody already has an idea what to the left means, or negative x direction if you wanted to use the standard xy coordinate system. And you know right, and you know up, and you know down, but there's also into and out of the page. So we use an x to represent into the page, and we use a dot to represent out of the page. Now sometimes I will write this like this. So this can be any vector. This could be the force into the page, it could be the velocity into the page, it could be the magnetic field into the page. All it is just a new way of writing an arrow that you can't write left, right, up, or down, right? Now you can even imagine this as like a really big, goofy-looking arrow. And if you imagine what this arrow is going to look like going away from you, this is what you're going to see. You're going to see these feathers on the back, like they'll make an X, right? If you can imagine it coming towards you, this is what you're going to see. So that's one way to visualize whether X or the dot means into or out of. So I can draw a magnetic field like this, and now you will know that this means the magnetic field is pointed into the page, and I can represent everything in 2 dimensions because this 3rd dimension is implied by the x's. Okay? If I have a charge moving to the right with some velocity, let's get a sense of what those numbers are going to be. We want to know what the force on our charge is going to be. Now, a pretty strong magnetic field would be around 0.25 Tesla. 1 Tesla is quite a bit of magnetic field. So a strong magnetic field, and then let's put a strong charge down too. So we know that this is going to be in maybe the microcoulomb range. Let's try 15 microcoulomb. And we really want to send this thing back at 1,000 meters per second. Maybe let's try 1,100 meters per second to keep it a little weirder. 1,100 meters per second, right? So we want to move this in the direction to the right, which means theta, in this case, is going to be exactly perpendicular to the direction of the B field. The velocity is exactly perpendicular to the magnetic field because the magnetic field is pointed into the page and the velocity is pointed along the page. In that respect, it didn't actually matter whether our velocity were anywhere else on this page. It will always be perpendicular to the magnetic field unless that velocity goes into or out of the page at least a little bit. So the plane of your screen represents everything perpendicular to the magnetic field, and so as long as this thing is moving in the plane of the screen, you'll get theta is 90 degrees. So we can calculate now the magnitude of force on this. Remember, sine of 90 degrees is equal to 1, so this gets out of the way. We have 15 times 10 to the negative 6 coulombs. We have 1,100 meters per second, and we have 0.25 Tesla. and that gives us about 4.1 times 10 to the negative 3 newtons of force. Alright, that's not much, so, but that's okay. It is kind of a smaller effect than we normally experience with like the Coulomb force, right? But if you add up enough charge, you can really start to see those effects. This is the reason that Earth's magnetic field actually partially protects us from solar winds. So when you get a really big solar blast of particles, those particles are charged, the ones that are not light, are charged, and when they near Earth's atmosphere, they have a tendency to be deterred by the Lorentz force, which is pretty helpful. Another thing that we have to notice is that most of the things in nature that are charged are quite small. So when you're dealing with electrons and protons, then even a force of 4.1 times 10 to the negative 3 newtons can provide accelerations that are pretty significant. Another thing that we're going to be interested in is that the force is always going to be perpendicular to the magnetic field and the velocity. Again, we will learn that direction in the next video, but I want you to keep in mind right now that the force is always going to be perpendicular to both the velocity and the magnetic field. Even if the velocity and the magnetic field are not perpendicular with each other, the force will always be perpendicular with the velocity and with the magnetic field. Okay, so this is your introduction to the Lorentz force law. The applications for it are numerous, and so we're going to go into a lot of that as we continue. This drives the idea behind the electric motor, for instance. So lots of applications to this. In the next video, we'll talk about the direction, so you can get a sense of how to tell where this charge is going to go, not just with what force.